We are focusing on coordinated harassment detection on Blue Sky as our assignment 3 projects. The team is Kendall Miller, Leo Lee, Amy Chen, and myself, Tian Zhang. We implement a Blue Sky labeler that detects and labels potential coordinated harassment campaigns using a probabilistic three-signal detection model, extending our policy proposal from assignment 2. Next slide, please. Regarding the problem and the motivation, we want to silence the threat of coordinated harassment. The harm, coordinated harassment, often termed breaching, involves organized groups synchronizing attacks against individuals on the online platform. This behavior inflicts outsized harm, leading to psychological distress, the silencing of marginalized voice, and a significant erosion of trust in online platforms. So why Blue Sky is vulnerable in this case? The first being federated architecture. Content spreads across decentralized services faster than centralized moderation can react effectively. The second being quote post feature. While useful, this feature can easily amplify pile-ons and contribute to viral harassment campaigns. The last being manual reports. By the time manual reports are processed, coordinated campaigns have often already caused substantial damages. So our goal to develop an automated labeler that can flag potential coordination early in its lifecycle, striking a balance to avoid over-moderation while protecting users. Next slide, please.
Oh, sorry.
Regarding our policy, detecting patterns and not just focusing on words. So our core principle focus on to detect patterns of coordinated behaviors rather than just merely scrutinizing individual words or phrases in isolation. This approach helps differentiate genuine harassment from legitimate discourse. Our policy also focus on the framework is ABC framework proposed in assignment 2, which provides a holistic view of online interactions. It uses a coordinated score from 0 to 1 derived from a combination of temporal, content, and behavioral signals. The system applies probabilistic labels instead of issuing definitive judgment of harassment, reflecting nuance of online interactions. The last being our moderation philosophy is to empower users and platform labelers to configure their own actions. We solely provide transparent and explainable risk scores, allowing for customizable enforcement mechanism. Next slide, please. Regarding our label taxonomy and turnable thresholds, we have a score of 0 to 1 as mentioned previously. So from 0.75 to 1, it's highly confirmed coordination high risk. So we suggest an auto high action or collapse replies. Between 0.6 to 0.75 scores, it's a highly likely coordination attack. So we display a warning banner as a recommended suggestion. And between 0.4 to 0.6 is a potential coordination that's being flagged. So maybe soft labels or manual reviews are recommended. And anything below 0.4 is not related and not detected. Next slide, please.
All right, great. So now let me walk through the technical architecture behind our labeler here. So everything centers around our main module, policy proposal labeler, which handles the full pipeline from ingesting posts, pre-processing text, grouping posts by who they mention, and extracting our three signals, and then assigning these coordination labels. So we'll begin with pre-processing here. Each post in our CSV input is normalized with lowercase text, removing all punctuation and URLs, parsing timestamps, and then doing account creation dates, and then constructing n-grams for similarity testing. We chose CSV injection with synthetic data rather than the Blue Sky API because true coordinated harassment events are rare and they're hard to reliably surface and they're very rate limited. Because of that, the synthetic data allows us to systematically test edge cases and stress test our labeler in ways that the real data wouldn't allow within the scope of this project. Next, our grouping logic extracts at mentions and collects all posts referencing that same target. To keep this efficient, we sorted posts by timestamp and used a binary search to pull all posts within our 10-minute temporal window, avoiding a full scan of the entire database and making this step a little bit more scalable. Briefly on efficiency here, because it's built into our approach, we've restricted similarity checks to posts within the same target. And then we also rely on binary search for fast temporal lookups, and we use TF IDF vectorization instead of slow pairwise string comparisons, and these allow us to keep the computation lightweight even as that data set starts to grow. So next, we're looking at our probabilistic approach with our signals. So once all of the posts are actually grouped, our model evaluates them using three signal families. The first being temporal signal, which measures how tightly posts cluster in time and how many unique accounts participate. So that would be like a rapid burst from multiple users would raise this score. Second is the content similarity signal. This is our strongest indicator. So we use TF, IDF with that character level n-grams and cosine similarity to catch repeated phrasing, shared wording, and copy paste patterns, common and coordinated attacks. And then we'll also detect 3 and 4 grams to signal. Lastly, we have behavioral signals, which look at suspicious account patterns. So, new accounts under 30 days old, sudden posting bursts, and unusually high author diversity directed towards a single target. And then we'll combine these with a weighted average 50% similarity, 30% temporal, and 20% behavioral to produce a score between 0 and 1, which will map our uh, signals to potential, likely, or confirmed coordination labels, as we discussed earlier. In terms of limitations, our system can sometimes overflag high volume organic activism if people naturally repeat phrases. And then it may underdetect sophisticated attackers who vary wording or spread activity over longer time frames. So we also work with very limited metadata, so richer network or semantic context could improve this in future versions.
So for the testing setup, we have a 150 data set that includes we have constructed a diverse data set of 115 static posts. Each meticulously crafted with strong truth labels to reflect various scenarios of coordination, and then 35 are categorized as confirmed coordination, and then 25 indicating likely coordination, 20 showing potential coordination, and then the remaining 70 confirmed to have no coordination. And our data set also included comprehensive edge cases. So for instance, discussing activism from harassment, identifying bobbers and their patterns, detecting slower evolving pylons, recognizing positive support campaigns, and then of course interpreting sarcasm and nuanced language. And then on top of that, outposts were manually labeled using a shared rubric requiring full consensus, like we did in class. This ensures that it mirrors real-world platform behavior. And then we have 2 scripts to evaluate the performance. And please bring it on.
Onto our results in finding. In findings, our comprehensive testing yielded promising results for both the accuracy and performance of the coordinated harassment detection model. We found an accuracy of 72% for overall correct classification rate, a precision of 88.9% with high confidence in positive detections, as we had minimized false positives. In a bit of a trade-off, our recall was 51.9%, as we did have some false negatives, and our F1 score was 0.66. In terms of multi-class accuracy, we found accuracy across all label categories, including confirmed, likely, potential, and none, being as 54.7%. In terms of performance, our system demonstrated efficient processing capabilities, which would be critical for real-time moderation environments. For our processing time, we found 13.3 milliseconds per post while processing batches of 1,000 posts. And on to our next steps. Our next steps would be to expand the data set with real-world blue sky data, incorporate LLM-based semantic filtering, integrate actor network modeling, including shared followers and retreat clusters, have temporal context moving for slower distributed pylons, and also consider detecting names and references beyond just @ mentions.